Loud. Okay. So signal pathway is the path that the electrical signal that we're picking up the patient, how it eventually makes its way back to our computer screen. So the path that it takes, essentially you start from the patient and work your way back. So if you're having equipment issues or anything like that, you start at the patient, look at where the electrode is applied, make sure it's applied well, it's scrubbed, the electrode is clean, it's coming in good contact with the patient, you have enough paste or enough prep, whatever. And then you travel it back to the head box and make sure it's plugged in correctly. Then the head box connects to the shielded cable, so making sure the shielded cable is plugged in, and then that travels its way to the amplifier, so making sure it hasn't become disconnected at that component. And then from the amplifier, the signals travel via cables through the wall to our computer. So essentially, it's out of our hands once the signal hits the amplifier. Up until that point, we can check the different components of the signal pathway to try to figure out where, if there's an issue, the issue might be going on. For those of you that did the senior testing with me, you pretty much saw, like, that's where I attacked a lot of the things, was along the signal pathway. Find the wire that's bad, and then follow the pathway to figure out where it's broken on that in that connection. Signal pathway, like kind of being able to follow the way the electrical signal travels from the patient to our computer screen. It's how we can follow, like, troubleshoot. You know, it's a really good method to kind of have it to be a little more methodical with troubleshooting when there's issues, to kind of start at the patient and work your way back. So let's talk about gain, sensitivity, filters. What I'm going to do.
So let's first back it up. We talk about biocalibrations. Biocalibrations are the calibrations that we have to do at the beginning of every recording. We're walking through the patient. This is on page 4 of this lab. We're walking the patient through, like, eyes open, eyes closed, blah, 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 blah. When we do a study, and this really comes back to the electrical theory, we first you have to hit start recording, and then what you have to do is an impedance recording. So it's recorded as part of the study. So that's where you see this here. That's an impedance recording. And then you're going to do the amplifier calibration, where it sends the 50, -50 microvolt signals to the amplifier, and you see it reflected on your screen. Do you guys remember ASM standards? The minimum length of the AC amplifier calibration has to be 30 seconds, and it has to be done at the beginning and ending of each study. Okay. And then once that's done and your signals settle out, we do biocals. But essentially, there are a series of calibrations that we do with our patients to test the integrity of the signals. So there's the amplifier calibration. There's the impedance recording. It doesn't really matter what you do first, as long as they're recorded as part of the study. So you can see the tags on the bottom. That's where we have, when you tell the patient to do it, that's what you kind of mark it as part of the study. What kind of artifact is that in our respiratory channels? No. What happens when it gets like that? Yeah, squaring off, which means what?
Bang.
Not electrode popping. Yep, pen blocking or squaring off. It's the same thing. So essentially what's happening here is the channel parameters, we're not able to fully see the deflection of the channel. So we need to decrease the gain or increase the sensitivity to bring the height of the channel down so we can fully see it deflect within the channel. Does that make sense? Yeah. There we go. When it still does that after doing that, then you like when you still have that squaring off, then it could be like a bad belt and we would need to go in and adjust the belt. So what we first start by doing is having the patient lie still with your eyes open. Usually how I'll say this is lie still with your eyes open. You can just focus on a point on the ceiling. It's okay to blink. So we do see blinks here. We see a blink here. We see a blink here, here. Essentially what you're trying to get is a 30-second kind of sample of what the patient's brain waves look like when they're relaxed, awake with their eyes open. Because if you look at that, that looks like almost theta, right? Because the amplitude is so small. So it's nice to have these to refer back to when, as a comparison when you're staging. Then you have them lie still with their eyes closed. So you can pretty much see where the deflection changes. And you can usually see if there's going to be some alpha. If alpha starts to come up, there it is. And then you might see some slow rolling eye movements, that type of thing. And obviously, they probably swallowed here. That's how a swallow tends to look, as you see that deflection on the jaw. So this gives us, you want to do it for 30 seconds or a full epic, and that gives you a nice kind of sampling of what their brainwaves look like, relaxed, awake with their eyes closed. So you can get an idea of what their alpha might look like. We have them, and then I'll tell them, open your eyes back up again and looking with just your eyes. Don't move your head. Look up and down a few times. So the reason why I say that, tell them don't move their head, because if they do look up and down, you're just going to get a lot of muscle movement. And what we really want to see is for them to see them roll their eyes up and down. And the eyes open, eyes closed are really the only thing you're going to do for a full 30 seconds. Everything else, you can kind of, once you see what you need to see, you can move on. So here we see them rolling their eyes up and down. And then I have them, okay, now look left or right. And that's where you see it kind of crisscross. I usually have them do it about 4 or 5 times. And then I have them blink 5 to 10 times. And depending on how quick they go or how slow they go, you can see the blinks. So the eyes are looking great. When you don't offset the eyes, if they're pretty much even, you're going to see like a limited deflection, especially like in here. So that's where it is important to do the correct placement for your eyes. What I'll have them do, the next one is the jaw. So usually you'll see a few different options there: teeth grind, yawn, swallow. Like, you don't want to say everything to them, or else it's gonna, that's a lot of things to do all at once. I usually tell them to do one thing, and then if it doesn't cause that deflection in the jaw, depending on how they flex the muscle by doing that one thing, then I'll move on to the next. Like, okay, just try grinding your teeth or clench your jaw. And if it doesn't cause that change in the muscle tone the way I want to see it, the way I expect to see it when you flex those muscles, then I'll move on to the next thing. Okay, give me a big swallow, because sometimes it, like, doing that kind of flexes the muscles, or a big yawn and it tenses those muscles. So essentially with this, when you tell them to flex the jaw muscles, you want to see that reflected on your chin EMG. So the chin EMG is one of those channels that, especially if you're not really familiar with what you're looking at, remember, impedances don't tell the whole story here. So you want to make sure that you are testing everything to make sure that it's working. Like, not only can it have a good impedance, but sometimes a good impedance, you still get a crap signal. So that's where you have to do these kind of instructions to have them do these things. Then what we do is we'll have them breathe. I'll tell them, like, breathe normally, or some labs have you breathe in, like, take a deep breath and let it out. And essentially you just want to check the integrity of your respiratory signals. Make sure they're all deflecting in the same direction at the same time. If not, you might need to adjust the polarity of the channels. You don't necessarily have to go into the room, but you might just need to, like, you can click on your channel properties and change the polarity or invert it. That would make it go upside down, or I would uncheck that and it would flip it to the other side. Have them hold their breath. So when you have them hold their breath, this is something that you need to continually watch the patient doing. Because you don't want to just lose track of time. It's really easy to get, like, fixing things or getting your paperwork set up. And usually I tell them to hold their breath for a slow count of 10, because you tell them to hold their breath for 10 seconds. They usually hold it for 3, because nobody really knows what 10 seconds is. So I usually tell them just hold your breath to a slow count of 10. And then sometimes the patients will want to hold their breath and they'll think a slow count of 10 means 30 seconds. So okay, it's all right. You can breathe. And essentially what we're doing here. So what is this mimicking? We have, let's first start here. No flow. Flow is flat line. What does that mean? What would that meet the definition of? Zero airflow for at least 10 seconds. Apnea. Then if we were to look at the respiratory effort and we see flat line, zero effort, what kind of apnea is that? Central. Yeah. So we're basically having them mimic what a central apnea would look like. So we're having them do a bunch of different kind of respiratory measures to change and mimic different things. We have them breathe through their nose. So you want to make sure that your flow signal continues to go when they're breathing through their nose, especially like your nasal pressure, your thermal. You want to make sure it's going to work when they're nasal breathing. And then you have them breathe through their mouth only. And typically too, you might see the muscle tone come up or even drop a little bit depending on the flex. Like you'll usually see that change. And you just want to make sure that you continue to get an airflow, like a flow signal when they breathe through their mouth. If you don't, that means you need to go in and adjust the mouthpieces. Like, you know how your flow sensor and your can like usually have little mouthpieces. You need to go in and adjust it. This is a CPAP study, and it's a nasal mask, I'm assuming, because when the patient breathes through their mouth, it like flatlines. So we're not getting a flow signal, which is totally normal. Then we have them point and flex their left foot a few times at the ankle. So you get that muscle flex on the left foot. And then I do it on the right to test to make sure that I plugged them in right, left and right. Or you can also watch them in the video and make sure they're flexing the right foot and the left, like don't have their left and right mixed up, but that we're seeing the movement. Because again, impedances don't tell the whole story, and we can tolerate higher impedances on legs. We can tolerate a little 60 hertz artifact in the leg leads because it's anticipated, it's normal. As long as we're getting and we can see what we need to see, which is if they were to have that muscle tension, we see it. So it's not really worth scraping and scraping and scraping this leg signal here to get it even skinnier than it is, because I can see my signal when the patient flexes their legs. Like, it's not impeding me from seeing it. We have them snore a few times. So you want to listen over the intercom when you have them snore. You can either I usually tell them to make a fake snore. Sometimes you can say, some people prefer like, oh, count to 3, one out loud, something like that. That's why it says snoring and counting. I wouldn't do both. I like to have them snore just so I can kind of get an idea of like a true picture of if they do snore. And what you want to do is listen through the intercom and make sure that what you're hearing is adequately reflected on the snore signal. So if I were to hear this really loud snore come through and see this tiny little blip on my snore signal, then I know I either need to adjust where the snore sensor is or maybe play with my gain a little bit here and increase it up so that it's better reflected, right? Because it looks pretty flat. If I were to see like, you just want to make sure that it's adequately reflected. And then the last thing that we need to test, because we've got to sample the brain waves. We've done a bunch of eye exercises. We've tested the chin muscle tone. We've tested the snore, the legs, the breathing. The last thing we're going to do is one more exercise with breathing, which is we're having them hold their breath, but while they hold their breath, push your stomach in and out a few times. And so essentially, pretend this is 10 seconds. So we have 10 seconds of no airflow. That's the definition of a apnea. Continued movement in the belts. So what kind of apnea is this mimicking? Obstructive, yeah. And this is actually mimicking like the paradoxical motion that we see during obstructive apneas, where typically when we breathe, our chest and our abdomen are in sync with each other. But when you're struggling to breathe against an occluded airway, you have that like obstructed or paradoxical motion of breathing where you see the chest and the abdomen belts get out of sync with each other because you're struggling to breathe against an occluded airway. So this one is the special one that you're going to have to explain. Like, you can't just say, okay, paradoxical breathe. Like, you can't just always read the labels. Like, it's more for us to just tag what we're asking the patient to do, but getting down to a way of explaining it well to the patient. And then I am like, okay, you're all set. Go ahead and go to sleep. Turn off where you need to. This is obviously the movement of them getting into position. And then once the signals settle out, that's when I'll tag lights off, what position they're in, if I'm on PAP, what my starting PAP is, anything else like that, and kind of start the study. So that's the process of BioCals. This is Sandman. So I'm going to show you, I can't do them on this computer because it's not a collection computer, but I'll show you how to get to them. Basically, oh, it's not even an option. One of the options up here, right up here, is calibration. And that's where you can get to all your calibrations on Sandman computer. You can get to your AC amplifier cal, your biocals, your impedance test. It's all under, like, there's an option up here where it's one of these, but I don't have it because it's only analysis on this computer where it says calibration. On the bed 2 and 3 computers, they're like the little buttons. You guys know how to get to the impedance test by this point. The amplifier calibration is the button right next to it, and then the biocals is just a drop down. So as you say it, you can click it. And it's just a matter of learning how, and we'll show you how to use the intercoms too, so you can talk through it. I'm gonna let you guys do like the lab activity on this lab. So let's jump. We talked about signal pathway, gain, sensitivity, and filter settings. Let's jump to that, page 2 of this lab. So gain, sensitivity all refer to the height, right, of a wave. I am recording, right? Yeah, yeah. Okay. So when we talk about gain and sensitivity, it really refers to the height of a waveform when we need to adjust it. So for instance, the abdominal belt and the chest belt are squaring off again. We would want to increase or decrease the gain. Decrease. So you want to decrease the gain, so bring the height of the waveforms down. On Sandman, there's a really beautiful way to do it where you just right click and do scale channels, and it automatically adjusts your gain for those channels for it. Another way to do it is if you just need to click on the channel, you can upwards or downwards. But the fact that it's still squaring off shows me that it's probably a bad belt. Like even after scaling it, it's still squaring off. I would need to go in and adjust the belt. So most have like the ability to change the height of it. Like you don't really want to play around too much with like the height and everything because it's oftentimes automatically set. But like for instance, EKG, sometimes EKG shows up on your screen kind of small. I like it big. I want it big. I want it in my face, middle of the screen, red, whatever color that's going to slap me in the face because it's something that you don't want to lose sight of at all throughout the night. Like, so I want it big in my face. For the most part, I don't really adjust the height or anything of any of the other channels except for maybe the respiratory channels to get them so that they're fully deflecting within the channel parameters. So when we go work through this page, I'm on page 2 of this lab. So remember, sensitivity is inversely related to height because sensitivity is a reflection of basically your sensitivity setting is whatever the voltage coming through from the signal. It's a display of how big it's going to be on the screen. So it's inversely related. So the more you turn up the sensitivity, the shorter the screen is going to be. Remember that triangle? It relates back to that one equation. Settings, filter settings. Let's review those. Just remember, we have the notch filter, the 60 hertz filter, which is automatically reduces frequencies coming through in the 59 to 61 hertz range, which is what our wall outlets operate off of. So it's automatically reducing like that electrical interference. It shouldn't be something that's standard that we put on every patient every time. Ideally, if you're doing a quality hookup, there's no need for the notch filter, but there will be instances where you need to apply it. Like for instance, if your legs you're getting a lot of 60 hertz or it, and it's just not worth scrubbing your patient anymore, you can just do the notch. So again, you would just come here, software filters, see it's already checked. Some techs will automatically put the notch on, and that's not really what you want to do, but ideally putting the notch, if you have a quality signal, putting the notch on or taking the notch off really isn't going to make a big difference in the quality of the signal itself. High frequency, low frequency filters. Let's review those. Remember, your high frequency filters, that's the upper limit of what we're seeing on the screen. So it's also known as your low pass filter. I'm going to talk with my hands a lot, so I can turn on my camera actually. How do I do that again? I don't know. Can you see me, Svetlana?
Yes.
Okay. I just don't know if it'll be easier because I talk with my hands, if it'll be easier to watch me talk with my hands. Okay, so your high frequency filter sets the upper limit of what we're looking at. It's also known as your low pass filter. So essentially any frequencies above it are blocked and every frequency below it are allowed to pass. So it creates that upper limit. Your low frequency filter is also known as your high pass filter. It sets that lower limit for what frequencies are allowed to pass. Everything set above it can pass, everything below it gets blocked. So it creates this window for each of the channels of what filter or frequencies we are seeing for that particular channel. And it really creates the window for the typical frequencies that physiologically is normal for that thing, for that particular channel. Like for instance, EEG. Physiologically, the normal frequencies of our brain waves are anywhere between 2.5 and 15 to 18 hertz at its fastest. So we create this window that everything within these filter settings would be normal. Anything outside would be abnormal and typically artifact or not physiologic for brainwaves. Does that make sense? This is like a better review now that you have a better handle on the basic principles. Okay. So filter settings. If we were to turn off our filters, if you have a really quality signal to begin with, it shouldn't make too much of a difference. I'm going to do it to F4. So we have the low frequency set at 0.3, the high frequency set at 35. Let's turn off the high frequency. It's allowing a lot of electrical interference to come in now. You see that? But if I were to turn it down to 20, doesn't look right. $35. The low frequency filter, when you have a lot of sweat artifact, what you can do is to increase it. So like when you're scoring and you have that squaring off happening in your EEGs, you can increase your low frequency filter and that'll decrease that sweat artifact. So you see how it takes out a lot of do you want me to change the color of the signal so you can really see which one I'm playing around with? I don't know. Let's make it pink. So you see how it really takes out a lot of the sway and bump of that channel in particular. So when you are staging, like there's not really much we can do with artifacts after the fact. Ideally, when we're running a study, we're fixing them as it happens, but after the fact, we can only filter and do what we can digitally to correct it. So you can change your low frequency filter settings if you're seeing a lot of sweat artifact. Like you guys saw. So basically all I did was I double clicked on it and it brought up my channel properties. I went to software filters and increased it to 1. You can also just right click on it, edit channel properties. Sorry. Same way to get to it or double click it. If you want to do it to all your channels, I just hold down the top one, click the F3, hold my shift key and clicked bottom one and then right click, and I can do it for all of them at the same time. Pretty much the only way, you never need to change your high frequency filter. You would only need to increase your low frequency filter if you're seeing a lot of sweat artifact. You can get a lot of sweat artifact in the eyes as well. I typically kind of don't apply my low frequency filter to the eyes though, because it can filter out the natural slow eye movements. And the purpose of the filters is to only temporarily change them. So I always kind of like to have like a look back so the eyes I can kind of tell if they're no longer having that sway in them. Then I know the sweat has kind of ended. Maybe they were having a hot flash or something. And if I wanted to, I can turn my low frequency filter back to 0.3 for the rest of them. Some techs, though, they'll automatically increase the low frequency filter because it does just take that bounce out and make it a little bit easier to read. Let's play with the gain or sensitivity on EEG. Remember I said you should never adjust the gain or sensitivity on EEG. When I see you guys open that up and start playing with that, it can really obscure what you're looking at and pretty much like make you change what you think you're looking at. Like, does that look like stage 1 still or wake, or does that look now like sleep? Because it looks like you have such a high amplitude, right? So you should never adjust your gain or your sensitivity. And it can work the same way where maybe we do have slow wave sleep, but we make it so small that it looks you're second guessing what you're looking at. So you always just kind of want to take it as it comes. All right, so we're going to go through some different, so we changed the gain setting, change the sensitivity. So sensitivity or gain, they're used interchangeably. It really just depends what type of channel. Gain is typically used for your DC amplifier channels, which would be like your respiratory, your snore, your sat. Sensitivity is used for your AC amplifier channels. So, but that's why those terms are just used interchangeably. They really refer to the height. Let's increase our high frequency filter to 70. Basically, what it's allowing is more of the electrical interference coming through because it's higher than that 60 hertz limit of, so it's allowing 60 hertz to pass through. Does that make sense? Let me explain high frequency filter again and why we see the change we see. Okay, high frequency filter, remember, sets your upper limit. So it essentially creates the upper limit. Anything below it is allowed to pass, everything above it is blocked. On our EEG, the high frequency filter is set typically at 30 or 35 because anything above 30 or 35 hertz that would come through through your EEG wire is not typically physiological brain waves. It's artifact, which means it's outside of what we want to see for that specific channel. So when I increase, and I'm just going through the lab kind of activities that are here. When I increase my high frequency filter to 70, it's now allowing instead of blocking anything above 35 from 35 to 70. So at 35, any frequency coming through above 35 is blocked. When I increase my high frequency filter to 70, it's now allowing only blocking anything above 70, but allowing everything below 70 to pass. And so what it's allowing to pass now is a lot of like this ambient electrical activity that in the US runs around 60 hertz, which is why you see this kind of thickening of the line. It's almost like because it's so fast, you can't see the individual up-down nature of what's happening there. So when you get 60 hertz artifact in a channel like that, it just looks thick. And so that's how you know that it's actually like an electrical interference. By staging, you should start kind of getting an idea of what looks normal and then what looks abnormal. Because what you'll also find too is like as the studies are running, there's a lot of times where we won't fix something. It's just not worth the detriment to the study. It's not worth waking the patient up. So say that were to happen on my, like where I would start getting a ton of artifact in one of my EEGs, I would just get rid of it. I would just like click on it and hit my delete key. So it's not even in my screen messing me up what I'm looking at. And so you'll have that too on the studies as you're staging. So we're going to decrease the high frequency filter to 15. So it's going to really limit. So we have such a narrow window right now of the frequencies that will be allowed to be displayed on this channel. Now it doesn't overly change that channel from what we typically, from what's normal, right? It actually looks a lot like the other channels, and that's because the frequency coming through on this channel right now is probably around 10 hertz. So a high frequency filter of 15 hertz isn't really limiting physiologically what's coming through. Make sense? Okay. I'm going to turn the high frequency filter back to normal. So you can see normal. Then we're going to raise the low frequency filter up to 10. So it's really limiting. So what we're seeing, right? It really pretty much took a lot of the natural normal frequency that should be coming through and it took it right out. So that's your low frequency filter. It's not fully turned off, but it's at 0.01, which is the lowest we can turn it to. Doesn't really have too much of an effect on it, right? You do see a lot more of this bump and sway in this one than you see in the others, like that artifact from the eye movements, or if the patient were to sweat, we'd probably see it a lot more in the F4 channel than we would in the other channels. Remember, low frequency blocks lower slow frequencies. So nothing's really getting blocked at this point, but if there's not a lot of artifact to come through, it doesn't really impact what we're looking at. I want to try to find an example to like do the notch. Actually, let's do it on our EMG. No, no, no. Doesn't really make a difference. So one trick that you can do is if you have like, you see how this is all thick right here? And it's from movement, but sometimes when a patient first goes to bed, you get like a lot of thickness and you're like, am I getting a bad signal? Is there a lot of 60 hertz coming through? What's going on? Sometimes what you can get is the thickness from like muscle artifact if the patient's really tense. And it can very easily be confused with 60 hertz artifact. So one way to differentiate 60 hertz from muscle is just try throwing on your notch, see if it makes a difference. It didn't. So it's not muscle, or it's not electrical interference, it's just muscle. See that? So I know that, like, okay, there's nothing I can do about it. The patient just needs to calm down. It will happen where you'll have a patient be tense in the beginning of the night, and even when you guys are in there and stuff, like you're tense and you can see that on the EEG. It doesn't come through on the impedances. Your impedances will still be good. It's picking up like the tension of your muscles. You realize you have muscles on your scalp. And the point like that's what I'm saying though, is that impedances don't tell the whole story, because your impedances will be fine, but your signals will look kind of really thick. What you can do is you can try throwing your notch on, see if it makes a difference. If it does, then you know it's electrical interference. We need to troubleshoot and fix that wire. Follow the signal pathway, get it fixed. But if it doesn't make a difference, then it's muscle artifact and we can let it go. Make sense? Okay. Montage, configuring a montage. That's page 3 of this lab. So the montage is the configuration of all the channels, like what we're looking at, and the standard settings that the channels take, the standard filter settings, sensitivity, blah, 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 blah. And they're all preset. So on Sandman, how you can adjust the montage is you can adjust each individual channel, whatever you need to adjust. There's so many different options we can adjust here. You can adjust the filter settings. You can add your threshold lines. You can change what the channel is referenced to. So say, for instance, M1 were to fall off. We now need to reference everything to M2. This is where we would do it. We can change the referencing to M2. Or say, for instance, we have a lot of EKG artifact. Remember, EKG double referencing is only beneficial for EKG artifact in your EEG and EOG channels. Basically, what happens with the EKG artifact in your EEG, EOG is where the M's are. The M's are picking up the pulse beat. Sometimes you have it worse in one than the other. So what you can do is avoid the affected one. So say it's worse in M1, we can reference everything to M2. Or if it's happening in both, which is common in patients with hypertension, we can combine the signal of M1, M2, or double reference or average reference, combine the signals coming from these two wires, and then let common mode rejection do its thing by eliminating the EKG artifact that's coming through from both. And how we do that is you just click average channels and you select, your M1, M2. Then it combines the average of M1 and M2. We can do that individually for each channel, whichever one you want to do. That's how you would adjust the montage in this. Kind of the general is what you're looking at, where it's plugged in, what its frequency, like the type, blah, blah, blah. Analog display is, where you can change the polarity of it. So check or uncheck, invert, we can change the color. Digital display is like, for instance, for the SAT signal, if you want a running number of what the SAT is, how often you want it. So that's how we can change all of this as you go through individual by individual. Kind of same way with our bed 2 and 3 computers is you can go individually, you just right click on them and you get the option to adjust like your filters, your gain, all of that through those channels on that. Or there's a way to do it all at once where there's a montage button to pull it up, and I can show you guys that in lab this week. I think like there's no way to actually change the gain sensitivity in these aside from like increasing or decreasing the arrow, doing it that way. So in this example, we just have a lot of artifacts. Let's get to it better. Here we go. We're missing a leg. We need our left leg. What artifacts do you guys see? EKG. Is it which channel is it most predominant in? Where is it coming from? Say F4 to M1. Is it coming from F4 or is it coming from M1? M1. So you notice how all the channels that are referenced to M1, the EKG is a lot more predominant in. The channel labels tend to be slightly higher than the channel. So it's mainly an M1. Study's already done. We can't go in and fix it. But what we can do is avoid the affected electrode, which means we could reference, change from referencing everything to M1 to M2. That improved the signal, right? Because M2 isn't nearly as affected as M1. Or what we can do is average reference. So combine the channels of M1 and M2. And common mode rejection kind of does its thing and eliminates the like signal because the EKG is slightly coming through on M1, M2 as well. You can see it a little bit, right? The thing I notice is like the chest belt is pretty flat. You want to adjust it at its source, but you can also try changing the gain. So I'm just going to scale the channel, see if it fixes it. It does. It's still, see how it's kind of still choppy though? It's not great. So probably would need to fix at its source if you could. The other thing I notice is nasal pressure is kind of going opposite of the other channels. So I'm going to flip it. And that flips it around. So they're all going in the same direction at the same time. I'm going to apply my notch on my EMG. See if that makes a difference. See how it cleared it up a lot? You got that thickness coming through. Especially on your chin EMG, recognizing 60 hertz, which is kind of common, especially the way your filter settings are on your EMG channels. Your low frequency is set at 10, your high frequency is set at 100. So it allows for it's within the range for electrical interference to come through. On the chin, though, like it's so important to get that kind of change. The muscle tone changes are kind of related to the patient's wake, sleep, whatever. So it's easy to miss if there's 60 hertz coming through on it, which is one of the reasons why biocals are so important to check to see, like, when you tell the patient to crunch, are you seeing that? And one of the reasons too, like why I'll usually when I'm staging, I'll have whatever both derivations of chin up that I can, but you tend to, as you go on, you tend to notice that one chin is a little more accurate at showing the deflections than the other. And then I tend to more look at that one versus the other. The legs are usually pretty easy to see if there's 60 hertz in them because they're either thick or they're not. When they're thin like this, they're good. But when they're thick, like, okay, there's some 60 hertz going on. This is pretty much configuring the montage, what we've been doing, playing out the gain settings, the filter settings. You guys remember what sampling rate is? I'm gonna take your silence as a no. Do you know, Spence? Yep. It's the minimum, it's the amount of times that the signal from the patient is sampled or read. So it's not like a continuous stream of information that's coming through. Like just think of like a video, the video quality. Like you get these videos, like security videos, where it's a very jilted kind of video. That's because the sampling rate is low. It's only picking up so like maybe 5 frames per second. So it's kind of like a jilted video versus a camera that has a better sampling rate, a higher sampling rate. Maybe it's picking up 20 frames per second. It's a lot more smoother. You're getting a lot more of the pictures coming through. So sampling rate is directly related to file size. The higher the sampling rate, the bigger the file size for each of these recordings, but the better the quality of the study that we get. Sampling rate is preset. It's not anything that we can adjust or change or anything like that. It's built into these systems. Okay. All right. So that's pretty much calibrations, kind of a little review on signal pathway, gain, sensitivity, da da da. I just really want you guys getting your hands on these computers, practicing going through doing biocals when you do your setup and doing the AC amplifier calibration. You know, I spend some time on it in lab typically, but I usually like catch you guys when you're doing your setups to, okay, let's work on this now individually because it makes more of a difference for you to see it and do it on your own versus me showing you as a group. So that's one of the reasons why I wanted to get what I can done with these labs now. So this way in lab, we have more time. I want you guys doing your setups. I want you all to pass on Monday. I do not want to be rescheduling individually hour-long assessments. Like, nobody got time for that. So y'all are going to pass, right? Okay. So I covered